안녕하세요 여러분, 해리입니다. Today, in this video, I'm going to start integration. So recall what we are trying to do using calculus. So calculus is trying to look for some of the geometrical aspects of a curve. So from differentiation, we mainly looked for the gradient. So using the gradient, we could find the maximum or minimum point, local maximum and local minimum point, also some tangents and normals, and increasing or decreasing region of a function or concavity. Now in integration, what we are going to do mainly is we are going to look for the area under the curve. So like all the shapes we learned in elementary math, so we look for the area of every shape, right? So again, graph is a shape, so we're going to look for the area using integration. And let's see how that works. So again, we start with linear function. Oops. So if we have a linear function like this, and if we want to find the area under the curve, something like, for example, let's say we want to find the area between x1 and x2 here. Then since this is fx, so it's a linear function, but it's fx, so we have x1 as the y value and fx2. Right? So the gradient, we're not looking for the gradient anymore, sorry. So the area under the curve, so the question will ask you like this. So find the area under the curve enclosed by the function and x equals to x1, x equals to x2, and the x-axis. So it's this red region. And in order to find the area, so this is a polygon that we've already learned. So it's a trapezoid. So we add fx2, right, with fx1, because that's the bottom length, the upper part length, and we multiply that by the height, which is x2 minus x1, and divide by 2. So that's how we can find it, right? But like in differentiation, again, not every functions they are not in linear function, right? So there are a lot more functions in curve. And now what we are going to see is that we are going to find the area under the curve with the certain boundary. So again, let's say there's something like, so I'll use A and B for this case. So let's say we want to find the area enclosed by the curve, x equals to A, x equals to B, and the x-axis. So this part. Again, it's a curve, so we can't really apply what we know so far. So this is a straight line, that's why we know the shape, it's a trapezoid, and we can apply the formula, the formula of the area of a trapezoid. But for this, it's a curve, there's nothing with this, no formula for this area. So what we can do is that first we try to estimate the area. How? So the shape looks like this, right? And why don't we divide this shape into some rectangles? Like this. Then of course the area of the rectangles, the sum of the area of the rectangles will not be exactly the same as this area, but we can possibly estimate it, right? So these rectangles will be the approximation of the area we want to find. But not but, sorry. Also, so notice that all the rectangles are within the curve, within this region, but we can try to construct the rectangles outside the region. Something like this. So some of these rectangles will be larger than the area we want to look for, and it's still, again, this is also another way of approximation, and the area that we want to look for will be between them, like that. So what I'm trying to say is that to find the area of this region, what we can do is that we can construct some rectangles like this and like that, find these two, and then we can find the values between them. Then those values can be the approximation of this. But like in differentiation, we don't want approximation. So we want to find the exact value. So what can we do is that we use the similar idea like what we did for area of a circle that in the previous video. So remember, when we have to find the area of a circle, we divide this circle into infinitely many segments and make it like kind of an isosceles triangles, because if you divide this circle into infinitely many pieces, then this circumference, I mean the part of this circumference, will look like a linear part, right? So it will eventually look like a rectangle, right? We use the same thing. So what we can do is that using this exact region, what we are trying to do is that we make this into many pieces. Many pieces. Okay, so let's try to write down the equation that which represents the sum of these many rectangles. So we said the boundary is A to B, right? And let's call this small part here B x1, I don't think so, like that. So right after A, we write it as x1, and we write it as x2, x3 until xn. So you see it look like this. So A, that's where A is. Oops, that's where A is. x1, x2, x3, and so on to xn minus 1, xn, and to finally the B. So in order to find the area of this one rectangle, we can say that the width will be x1 minus A, right? So we want to find the area of the rectangles. Okay, so the base is x1 minus A. Now what about the length? So note that this function is fx, right? Then if we put so if the input is x1 here, then the length here will be fx1, right? Because that's the value of the function. So that means the area of the first rectangle will look like that. And using the same idea, we can make up the other rectangle. So we started from x1 minus 8, and the next one will be x2 minus x1 times fx2, and x3 minus x2 times fx3, and add all the way until xn minus xm minus 1 times f, let's say xn. Right, so something like this. Now we have too many variables, right? So we have like x1, x2, x3, x4 to xn, and of course we don't want too many variables. So what we can try to do is that why don't we make these width of all rectangles the same? And how do we do that? We make it as b minus a over n. And let's call this as delta x, because it's the change of x anyway, so let's call it as delta x. And note that we can use delta x, we have to use delta x here, we cannot use dx directly, because yet we haven't divided the rectangles, we haven't divided this region into infinitely many rectangles. We haven't done that. So still we have finitely many rectangles. Okay, that's why we have to use delta x. Dx is to represent that the change of x here is instantaneous, but yeah, it's not instantaneous yet, so we make it as delta x. Then all these terms, this change of x, they become delta x, right? Because again, I said that this represents the equal width, right? Equally divided width. So this is what we have for the area. And please note that that is the approximation, still the approximation of the area. So this area represents the exact value of area that we want to look for. So yeah, so this is still the approximation, and still there are too many terms. So let's try to reduce terms using some mathematical notations that we've learned. So they're all sums, right? And there's a pattern where these x1, x2, x3, these values increase by 1, right? 1, 2, 3, and so on to n. Then we can use sigma notation, right? So delta x, we just leave it, and then we make it as fxk from k equals to 1 to n. So that's the approximation of the area. Now, our aim is to look for the exact area, not the approximation. Then how do we use this to find the exact area? So I've already indirectly mentioned when I was explaining the difference between delta x and dx. So like the area of a circle, why don't we try to make these rectangles into infinitely many pieces? So how do I show that mathematically? So infinitely many pieces, that means this n tends to infinity, right? So yeah, this n, if this n tends to infinity, then there will be infinitely many pieces, right? So how do we write that? We've learned the notation, mathematical notation, limit, where n tends to infinity. And we write down the same thing. So sigma delta x times fx. Okay, actually I'll write delta x here. It will not affect the equation, but yeah, just to explain something later in a better way. So yeah, this is now the exact value of this area. And how is this related to integration? So this equals to the integral. So remember the boundary is from a to b, right? A to b fx dx. Okay, so now I'll explain one by one. This sigma is the same, has become the integral. Why? Because sigma, we use it in discrete variables. What I mean by discrete is that where you can, how should I say, where you can count the number, for example. So 1, 2, 3 integers are discrete. So natural numbers are discrete, right? 1, 2, 3, 4, 5. Integral, we use integral when the variable is continuous. What I mean by continuous is that, for example, where you cannot count the numbers. So, for example, 1, and what's after 1 in continuous? Maybe some say 1.01, but what about 1.001? And what about 1.0001? You can't count it, right? So for this, we call it as continuous values, and integral is used when you have to add continuous variables, okay? So the sigma has become the integral, and this boundary is the same. So remember, for this one, we just used the other notation to set the boundary, but since we already know the boundary in a and b, so we can directly use a and b. Okay, so this is the length of the rectangle, right? And delta x is the width of the rectangle. So these two multiplied together will give us the area of each rectangle, right? And what we are summing up is that we are basically summing up all the area of the rectangles. We're doing exactly the same thing. So fx from a to b, that means we are basically putting fa, fx1, fx2, but note that, again, this is continuous. So it's not like a, x1, x2, so on. It's just adding up infinitely many continuous numbers. So it's more like a line. But again, not again, but you must note that line does not have an area, right? So recall the use of limit. So like what we did for calculus, so that limit h tending to 0, h is not exactly 0, right? That's why we can put h in the denominator. If h equals to 0, then we cannot put it into the denominator, right? It's the same. This is just saying that n is very, very large number. It's not infinity, but very, very, very large number. Okay, so the width is as small as like it's a line, and you're just adding up all those like line looking rectangles. Okay, so this and delta x becomes dx because remember what we let delta x as b minus a over n, right? And when n tends to infinity, then what does value go to? So when you have a fixed number, b minus a is a fixed number, it doesn't have to be small, right? It's just a region, it's just a boundary. But when n tends to infinity, then that means you're dividing a constant by a very, very large number, then you will approach to 0, right? You can think. So 1 divided by 10, 1 divided by 100, 1 divided by 1000. As the denominator gets larger, the entire value gets smaller, right? 0.1, 0.01, 0.001. So but what's b minus a over n? It's delta x, right? It's delta x. And delta x, when n is tending to infinity, delta x approaches to 0. That's why we have this. So, okay, I'll write it better. So, limit delta x tends to 0, delta x equals to dx. And this is exactly what I taught last time in differentiation. So, this still holds here. So, that's how we can name all these variables. So, explain all these things in properties of this integral, okay? So now, if you have an integral like this, then you now know the meaning of this. So basically, you're trying to find the area of rectangles, right? So this is the length and this is the width, where you're adding from x equals to a to x equals to b, okay? So again, like in differentiation, if you see dx here, it's saying that you're integrating a function by x. Then, for example, if you have something like, so if you have a function of x, but if the question asks you to integrate by y, then can you directly integrate? No, like in differentiation. So for this case, what did you do? You use chain rule, right? For integration, well, you will have a lot of methods to do this, and I will talk about them later. So that's the definition of integration. And now the hard things are done. So always when you learn something new, the definition is the hardest. And since the definition is over, now everything should be easier. What I'm going to talk about now is that we have variety, how should I say, types. Okay, let's say types of integrals. Oh, one thing. So what I mean by integral is something like derivative, right? So what does it mean by derivative? It means differentiated function, right? So if you have first derivative, that means you differentiate it once, and second derivative, that means you differentiate twice, right? Integral means you integrate a function, but there's no such thing as like first integral or second integral. You just integrate once. But yeah, so again, integral means you're integrating a function, okay? So integrated function. So there are two main types of integrals. The first is indefinite integral. And second thing is definite integral. So like the word says, indefinite, that means it's not defined. What's not defined? The boundary is not defined. So that means this gives the equation of the area under the curve. So what I mean by under the curve is mainly it's just omitting that, it's saying that, it's indirectly saying that the area is enclosed by this area, this curve with x-axis, okay? So area under the curve, that means that region, okay? Then what about definite integrals? Must be the opposite, right? So it gives you the exact area. So it has, what it means by definite integral is that the boundary is defined. So you can compute the specific area under the curve bounded by a certain boundary. So that's what it means. First, we're going to start with indefinite integrals. before we directly go for indefinite integrals, if so for those students who still don't really get what the indefinite integral and definite integral is that, so you can recall what you did for differentiation. So if you have a function fx, let's say y equals to fx, and if you differentiate it, then what do you get? What's f prime x? What does that mean? It means the equation of the gradient of fx, right? That's why if we have a function like fx like that, and then if you want to find the gradient at a certain point here, let's say a, then what do? You differentiate the function. So you first find f prime x and you substitute this value, right? So you have the specific gradient at this point, right? What it means, what indefinite and definite integral means is that same thing. So indefinite integral, you're just basically finding this equation of something. So equation of the area under the curve, not defined, not at specific place. So that means once you have this, you can calculate the definite integral. So you're not doing something different. So even if you have to find definite integral, you have to do this first because integration works the same. It's just the two types of, so it depends on what you have to find. So if the question just asks you to find the integral, just integrate a function, then that means you find this. But if the question asks you to find the specific area bounded by a certain region, a certain boundary, then you look for the definite integral. That's it. So yes, indefinite integral. So all the formulas that we are going to do, all the formulas related to integration we are going to do are based on indefinite integrals. And there are some different methods to do integration. So mainly three for IB. So first, using the sense of anti-derivative. So remember, derivative means differentiation, right? So differentiated function. Anti, so you're doing the opposite, right? So that means you're doing what you have to do for differentiation. You're doing something opposite to differentiation. Second thing is substitution, integration by substitution. And the third thing is integration by part. Okay, so for IGCSE students, you just need this. But if you also learn substitution, it's going to be very useful. For SL students, so this is just for IGCSE students. And for IB SL students, you have to do until substitution. And of course, for HO, you have to do them all. Okay? Alright, so first, let's start with antiderivative. And one thing, for HO students, again, you have to do all. SL student, you have to do these two, okay? And IGCSE student, you just need this. But if you want to guarantee if you want to do very well in integration, then it's gonna be good if you learn substitution as well. Actually, I shouldn't have called this as 1, 2, 3. I'll call it as ABC. So first, let's start with. Okay, let's use the other paper. So. So main computation. So first, A using antiderivative. So unlike in differentiation, where we use the first principle to derive the different formulas for differentiation, for integration, well, you have a similar thing. So you have a similar thing, and this is called the Riemann sum. And I really don't recommend you to use this to find the formula because you haven't learned the infinite sum. So it's different with infinite geometric series. It's something else. So don't worry about the basic formula like in differentiation. Okay, so just remember that integration is the opposite way of calculating differentiation, but don't understand this like integration is the opposite of differentiation. No, because as you can see, differentiation is finding the gradient, right? And integration is finding the area under the curve, and they're not really the opposite, okay? Just the calculation is the opposite. So let's recall some basic differentiation rules. So if you had so let me just write this as differentiation, and we're going to do integration. So for example, if you had y equals to x to n, if you have to differentiate this, very simple, you know it, right? N times x to n minus 1. So again, I said that integration and differentiation are opposite to each other. So that means I'm not opposite to each other, sorry. So integration is the opposite of differentiation. So that means if you integrate this, you have x to n. That's what it's saying. One really important concept in indefinite integral. So see, there's no boundary. So this is an indefinite integral. And for any indefinite integral you do, you must put an integral constant c. And I'll tell you why. I'll tell you what the integral constant means. So, for example, let's say you have y equals x squared. Then, actually, sorry, for this one, I should. Oh, okay. Since I have to photocopy the notes as well, I'll just write the explanation here. So let's say you have an equation y equals x squared. Okay. What do you have if you differentiate x squared? You have 2x. Then what about if you differentiate x squared plus 1? And what do you have if you differentiate it? Still 2x. What about y equals x squared plus like a random constant pi? Then still you have 2x if you differentiate it. So whatever constant you have, no matter how large, how small, how negative, how positive it is, as long as it's a constant, you just cancel it out, right? You make it at 0 for differentiation. But if you have to integrate a function, so remember, integration is the opposite of differentiation. So if you have a differentiated function, that means if you integrate 2x, you have x squared. That's what this is saying, right? That means if you integrate 2x, you can possibly have x squared plus 1, x squared plus pi, x squared plus 10 to 1,000, any constant with x squared, right? And we don't know what that constant is. That's why we put the integral constant c, okay? And please remember to put this integral constant after you finish indefinite integral. Unless, otherwise, you'll get mark deducted if you miss this in a test or in an exam, okay? And well, I emphasize that we have to write c for indefinite integral because, yeah, you don't have to for definite integral, but still you have that constant. So even for definite integral, you still have this constant c, but later when you do some questions with definite integral, you can see that this c, this integral constant, cancels out. That's why we don't have to worry about it, okay? So yeah, that's the first thing that we see. And from this, let's try to derive one formula. So it's not really useful if we have something like this as a formula, right? We must have a function like this, and then we can make it to x to n, right? Then what about this? This is certainly, so if we have a formula for this, then this would be certainly better to apply in the questions, right? Because most of the case, the question will have a function in this form, not this form, right? And so in order to solve for this, so again, we try to use antiderivative. So what this means is that if you differentiate something, then you have x to n. Then you can think. So in differentiation, if you differentiate a polynomial, then you deduct 1 from the power. Then if you differentiate x to n plus 1, the power would be n, right? Because we subtract 1. But if we differentiate this, what do we have? n plus 1 times x to n, right? But we just want x to n. Then what do? We divide this by that constant out. Then, if we differentiate this, we'll have that, and this coefficient will cancel out with this. So if we differentiate this, we'll have x to n. And again, add this constant plus c, okay? So that's the first basic formula that you have to know. And there are some multiple things that we've also learned in differentiation. So for example, when you have a constant, let's say a constant with a function fx, then if you have to differentiate it, you leave the constant, right? And you just differentiate fx and make it as f prime x, let's say. Then that means if you integrate f prime x, if you integrate a times f prime x, then you have a times fx plus c. And one thing, so whenever you have a constant, you can move it out from the integral, like what you can for differentiation, right? So when you have to find dy over dx, that means we differentiate both sides by x, right? So first you write it as dfx over dx, right? And you just move out the constant. And dfx over dx will yield f prime x, and that's how we get the formula, right? It's the same. So whenever you have a constant, you can move it out, and then you just integrate the function inside the integral, okay? Now, some more thing that you have to do is that, oh yeah, this one, this. So when you have to differentiate a function with a multiple terms, then remember you differentiate it one by one, right? It's the same for integration. This will first become like this. Please be aware that you have to write dx, because this means nothing, because okay, you're integrating this, but with what? What are you integrating this with? Which variable are you integrating this function with? We don't know, right? So it means nothing. That's why we have to put dx, and that's why I've been emphasizing so much about the use of dx, the meaning of dx, dy, all those things in differentiation, okay? So again, like in differentiation, when you have dx in the denominator, what does that mean? We differentiate something with x. This means we integrate something with x, okay? So always put dx, or if you have to integrate with y, then put dy or whatever variable you have to use, okay? So anyway, to resume, so we can separate the integral like this into two different integrals. So what that means is that we just need to integrate term by term, like for differentiation. That's what we have, and again plus c. So these are the main things, the basic computation. So now when you have a polynomial, then you should be able to integrate it simply. So for example, if you have to integrate something like this. Oh, okay, sorry. Before we do this, sorry. One more thing. So for example, if you have a constant, right? Then if you differentiate it, oh no, not constant. So if you have cx, let's say, so a constant times x, then if you differentiate it, you have c, right? That means if you integrate a constant, you'll have, actually I'll not use c because we have to use c for the integral constant. So if you have to integrate a constant, then you will have ax plus c. And why? Because constant a actually means x to 0, because x to 0 is 1 unless x equals to 0. 0 to 0 is undefined. So x to 0 is 1, and x to 0, that means n equals to 0, right? So when n equals to 0, you see that 0 plus 1, right, denominator, then the fraction is just 1, and x to 0 plus 1, which is x to 1, right? That's why we have ax plus c. That's it. And so now we do the example. So if you have to integrate this polynomial, so first, using this, we have multiple terms added, right? So we integrate one by one. One by one. Okay, so for this one, it seems like we can directly apply this first formula. So the power is 5, x to 5. That means 1 over 5 plus 1. So 1 over 6. X to 6, right? 5 plus 1. And first, let's forget about c yet. So just leave it. Plus, alright, so for this one, we can use this second one, right? So where we have a constant, we can just move it out. So we move 3 out, and basically we are trying to integrate x squared, right? And again, x squared, we can apply this. So we have 1/3 x to cube. And again, let's forget about c first. It's not, we don't have to write it, but I'll tell you why. And lastly, we have 1, right? So if we have a constant, then remember, oh, actually I didn't write the, oops, no, right, so if we have 1, then we have just x, right? And now we put c. Then some may ask why don't we add 3 different c's? So for example, like c1 from this plus c2 from this and c3 from this. Why? Because again, c is just a random constant that we don't know, right? So it's just a dummy, it's just any constant. So why don't we just let c1 plus c2 plus c3 as just one capital C? And it's much better to see, right? It's at least we don't want to make too many variables. So unless it's necessary to differentiate these, what I mean by differentiate is not the differentiation, but distinguish these constants, then just make it as just one constant is also fine like that. Later in IBHO option calculus, where you have to do differential equation, well, even for HO-IB option, differential equation, you don't have to do it, but so later when you study differential equation in university, you have to do something like second order inhomogeneous differential equation, and for those cases, sorry, homogeneous differential equation, and for those cases, you have to distinguish these two, the constants by constants. But again, we're not university students, and you don't need that, right? So let's just keep it simple. So make it as C, okay? So that's the very basic method of integration, and seems like it's 45 minutes, and sorry, I have something to do later, so I'll end the video for today. So this is just for the basic integration that we've done. So we just covered indefinite integrals, not entire indefinite integrals, but like the basic of basic indefinite integrals. And what we are going to do next is that we are going to do some more functions. So we certainly learn some more functions like cosine, sine, or for example, exponential, ln x, all those things, right? So we are going to look for those integrations as well. And we also have to do some definite integrals and actual application of integration to find the area under the curve. And later, the final application, two final application, the volume of revolution and kinematics. So that's it for today, and see you guys in the next video. Bye.